Hey friends, ever wondered how your phone camera can identify plants or how automated greenhouses track flower species for research? In this video, we'll build a flower classification system from scratch using one of the most legendary datasets in machine learning, the iris flower dataset. But this is not just another ML video. We'll take it slow, explore the data deeply, visualize everything, and uncover insights like a true detective. Ready? Let's dive in. For that, let's bring in our team, Pandas and NumPy for handling the data, Seaborn and Matplotlib for visuals, and scikit-learn to give us the iris dataset. Now, we have 150 flower samples, each with sepal length and width, petal length and width, and the species types are setosa, versicolor, or virginica. Let's explore them. So, data cleaning and initial exploration steps are very important, and we do it using the info function, describe, and isNull, and also finding out if we have any duplicates or not. So, this great news, no missing values can be found, and there are no weird data types and no duplicates also. Think of this dataset like having a perfectly arranged flower bed in a lab. No weeds, no missing labels. And let's go into detailed exploratory analysis with some real world insights. Or how do you analyze the actual real world data, or how do you go through the data and drive and get insights with the data? Visualization helps us a lot with getting data insights, right? So here we have visualized the sepal length, sepal width, petal length, and petal width. So from all the visualizations, we can observe or draw insights that setosa has shorter petals and small sepals also, and whereas virginica tends to be longer and wider in both, so it's the highest in both of them. So most part of the flower is wide and long. Versicolor sits in between, so it's in between setosa and virginica. In real world, this can help farmers monitor crop variation, and scientists can detect hybrids, robots sorting flowers in greenhouses. And next, we can plot a pair plot. Look at this visual. It's like a fingerprint of each species. Setosa is completely separated. The blue color is indicated with setosa. So setosa is completely distinguishable compared to versicolor and virginica. There are some overlaps between versicolor and virginica. That's a real world challenge. Some species just look similar. Now, moving on to the outliers and the correlations and the box plots. So, for finding out the correlations, we plot the heat map. We first need to find out the non numerical column and drop them, and then form a heat map with them. Look, look here, the petal length and the petal width are highly correlated with the species. That tells us they are probably more important features. Sepal width, this seems to be a less important feature and less helpful, like maybe consider it as a noise data. Moving on to the box plots, this helps us identify the outliers that are there in our data set, or something that are weird data points that might cause skewing if there are more, and which might affect our final decision of predicting the target variable. This shows how each feature varies by species. These visuals help in quality control or research. If a new flower falls way outside the box, it could be misclassified or an entirely new variety because of predicting it in a wrong way. Now it's for us strategy time and deciding what features really matter. So, before building a model, let's ask questions ourselves. Which features separate species best? Are these overlaps that might confuse the model? So, based on the visuals, we can conclude or draw insights that the petal length and the width are gold. Whereas sepal width might be noisy. We'll use all these features first, but now we know where the signal is. So for now, we'll be using all the features, and we are going to drop the species, which is the target variable, from the X, that this X only contains the features. And we put all the target variable values in Y for testing purposes, training and testing purpose. And then we split the data into training data and testing data. The size of the testing that we have given is 20%, and the rest goes to the training. So it's just like teacher teaching students for a semester and then giving a surprise test. Now let's build our model. And we here build the decision tree classifier, which is used for training, building our model using the data that we are getting, like X train, Y train also. Now let's test how our model learned, how well our model have learned. So it is, the setosa is nearly perfect, like it is nearly equal to 1 and everything. So I think everything has been 1, and this matches our earlier visual insights. See how EDA guides our model decisions? And now let's visualize the decision tree that we have built. And here's the decision tree in action. Like a flowchart, it makes a split based on the petal length, and then the petal width, and the petal length, and petal width, sepal width again, and finally concludes whether it's a versicolor or virginica. See, if the petal length is less than or equal to 2.45, then consider it to be setosa. If not, then consider the petal length. If it is greater than 4.7, and then go to the 1.75 of petal width and draw the conclusions, and concluding which feature or which species the particular flower belongs to. That's how we draw conclusions using decision trees. Like, if not this, go to this. If not this, consider this and conclude this. So that's how it works. It's a wrap. So what did we learn today? How to explore the dataset deeply, and why EDA and visualizations matter, and how real-world logic helps you pick features, and how a simple data decision tree can be so powerful. Next steps are, you can try random forests, SVM models, and tune the hyperparameters and build a dashboard in Streamlit. If this video helped you, like, subscribe, and tell me, should we explore plant diseases or deep learning next? Until then, keep exploring and always trust the data. Thank you.